In this video, we are going to understand one of the most common reasons why Spark jobs look like they never finish: skewed data. When you run a Spark job, it's important to know how the system handles your data. In a normal Spark job, data is divided into partitions, and each partition becomes work for a task. When the data is balanced, every task receives a similar amount of work, and all tasks finish around the same time. This ensures that the job runs efficiently and completes in a reasonable amount of time. But with skewed data, one partition receives much more data than the others. That single partition becomes a bottleneck. One executor keeps running while the others are already finished or sitting idle. This imbalance can cause the entire job to appear stuck, even though Spark itself is functioning properly. The real problem is the data distribution. A few keys are holding most of the records, and one task is forced to process much more work than the rest. This situation often happens when certain keys in your dataset are overrepresented. For example, if you're processing web logs and a particular user has generated an enormous number of requests, that user's data might end up in a single partition. As a result, the task handling that partition will take significantly longer than the others, causing delays and making the job seem unresponsive. So when you see one task running much longer than the others, always think about data skew first. Identifying and addressing data skew can greatly improve the performance and reliability of your Spark jobs. Understanding how data is distributed across partitions is crucial for optimizing your workflows and avoiding unnecessary bottlenecks. Data skew occurs when a small number of keys end up owning the majority of the data, leading to an imbalance in processing. Imagine you have a large dataset with a key such as country. Most entries might be labeled as US, while only a few are marked as CA, DE, IN, or FR. This uneven distribution can create problems during data processing. When Spark performs a shuffle operation, it typically groups records by their keys using a hash function. All records with the same key are sent to the same partition. If one key, like US, appears very frequently, all those records will be directed to a single partition. As a result, that particular partition becomes significantly larger than the others. While tasks handling smaller partitions complete quickly, the task responsible for the hot key takes much longer to finish. This delay can slow down the entire process and reduce overall efficiency. This issue is not caused by a problem in Spark itself, but rather by how the data is distributed. It's a common challenge in distributed computing where workload isn't evenly spread across tasks. Understanding and addressing data skew is essential for optimizing performance and ensuring smooth processing in large-scale data applications. Spark parallelism depends on balanced partitions. When the data is evenly distributed across partitions, each partition contains a similar number of records. This ensures that every executor receives a comparable amount of work, and all tasks remain busy throughout the processing. This is the ideal scenario because it allows the cluster to utilize its resources efficiently, avoiding bottlenecks and ensuring smooth performance. On the other hand, when the data is skewed, one or more partitions may contain significantly more data than the others. This imbalance leads to a situation where a single partition is assigned to a heavy task, which takes much longer to complete. Meanwhile, other tasks might have already finished, leaving some executors idle and underutilized. This uneven workload distribution can slow down the entire process and reduce the effectiveness of the cluster. This is why skew can be very problematic in production environments. Even if you try to improve performance by adding more executors, increasing CPU power, or allocating more memory, the issue of a hot key, meaning a specific data key that is overrepresented, can still cause one task to become a bottleneck. Simply scaling up the cluster does not solve the root problem. The real solution lies in adjusting how the data is distributed or redesigning the operations to handle imbalances more effectively. By addressing the underlying causes of skew, you can ensure that the cluster operates at its full potential and delivers better performance overall. Data skew usually appears in operations that require data with the same key to be collocated. This happens when certain keys are disproportionately represented, causing some processing units to handle significantly more data than others. This imbalance can lead to performance issues and bottlenecks in distributed systems. The first common place is group by or aggregation. When performing these operations, if one group contains a large number of records compared to other groups, it can result in a single task being overloaded with work. This can slow down the entire process and affect system efficiency. The second place is join keys. If many rows have the same value for the join key, those rows will be grouped together, potentially overloading a specific partition. This can cause delays and uneven distribution of processing load across the cluster. The third place is window functions using partition by. When a particular window partition contains an excessive number of rows, the computation required for that window can become very slow. This can impact the overall performance of the query and delay results. The fourth place is deduplication. When there are many records with the same key, removing duplicates can create uneven workload distribution. Some partitions may end up handling a much larger amount of data, which can slow down the deduplication process. The fifth place is time-based keys, like processing data by date. A busy day, the end of a month, or a default timestamp can all result in a hot partition. These events often lead to a concentration of data in a single area, creating performance challenges. Typical hotkeys are values like country equals US, status equals active, null values, or default values. Skew often hides inside normal business keys, making it difficult to detect without careful analysis. Identifying and addressing these skewed keys is essential for maintaining efficient and balanced data processing. The easiest way to recognize skew is by looking at the Spark UI. When you open the stage details, take a close look at the task duration. If most tasks finish in a similar time, but one task takes much longer, that is a strong signal of skew. This can be easily spotted because the bar representing that task will stand out compared to the others. You may also notice that some executors become idle. This happens because they already finished their tasks, but the full stage cannot complete until the slowest task finishes. As a result, those executors are left waiting, which is a clear sign that something is not balanced. Another symptom is long garbage collection time on one executor. This usually means memory pressure because one task is processing too much data. When an executor has to spend a lot of time cleaning up memory, it can significantly slow down the overall process. You may also see more spill to disk. Spill happens when Spark does not have enough memory for the operation and starts writing temporary data to disk. This is a sign that the system is struggling to handle the workload efficiently, and it can lead to performance issues. The key idea is simple. If one bar is huge in the Spark UI, skew probably exists. It's important to identify and address this early to ensure that your Spark jobs run smoothly and efficiently. Now let us create skew on purpose so we can see how it behaves. This exercise helps us understand what happens when data is not evenly distributed across keys, which is a common issue in big data processing. By intentionally creating an imbalanced dataset, we can observe the effects of skew and learn how to handle it effectively. In this example, we create a list called data. First, we add 100,000 records with the same key, hot key. Then we add only 1,000 records with different keys like key 1, key 2, key 3, and so on. This setup ensures that one key has a massive number of entries compared to the others, making it a clear case of data skew. After that, we create a data frame with two columns, key and value. The key column contains the various keys we've added, and the value column holds corresponding values for each record. This structure allows us to analyze how data is grouped and processed. This is a perfect setup for skew because one key dominates the data set. Most records belong to hot key, while the other keys have very few records. As a result, when operations like joins or aggregations are performed, the system may experience performance issues due to the uneven distribution. This type of dataset is useful for demonstrations because it clearly shows what happens when one key receives most of the workload during a shuffle. It highlights the importance of balancing data and optimizing processes to avoid bottlenecks. Understanding these scenarios helps developers and data engineers design more efficient systems. Now we trigger a shuffle using group by. This process involves grouping the data frame based on the key column, which allows us to count how many records are associated with each unique key. Once this is done, we display the results and take a closer look at the execution plan to understand how Spark handles the operation. A group by operation is considered a wide transformation because it requires data to be redistributed across different partitions. This means that all records sharing the same key need to be gathered in one place, which can lead to significant data movement. During the shuffle phase, the data is reorganized based on the key values. For regular keys, this results in smaller, manageable partitions. However, when dealing with a hot key, meaning a key that appears much more frequently than others, it can create a single, extremely large partition. In the execution plan, you typically see an exchange step followed by a hash aggregate step. The exchange step indicates the shuffle process, where data is moved around to ensure all records with the same key are grouped together. The key takeaway here is that a hot key can cause one specific aggregation task to become very heavy. This single task might slow down the entire stage, as it takes longer to process compared to other tasks. Understanding this helps in optimizing performance and avoiding bottlenecks in distributed data processing. One common strategy to handle skew is called salting the key. This technique helps distribute data more evenly across partitions, especially when certain keys are overrepresented. Before salting, most records for a specific hotkey end up in the same partition. As a result, that particular partition becomes overloaded, while other partitions remain underutilized or cold. This imbalance can significantly slow down processing and reduce system efficiency. After applying salting, a random number is added to the original key. Instead of just having hotkey, we create artificial keys such as hotkey 0, hotkey 1, hotkey 2, and so on. These modified keys help split the data associated with the original hotkey into smaller chunks. By doing this, Spark can distribute these smaller keys across multiple partitions, preventing any single one from becoming a bottleneck. As a result, the overall workload becomes more balanced, and the system can process data more efficiently. However, salting introduces additional complexity into the data pipeline. After the initial aggregation step, it may be necessary to perform a second aggregation to merge the results back into the original key. This extra step ensures that the final output remains accurate and meaningful. While salting can lead to performance improvements, it's important to carefully manage the process to avoid errors. The added complexity requires careful planning and implementation to maintain data integrity and correctness. Another clean strategy is using a broadcast join. When one of the tables involved in the join is small enough, Spark can efficiently distribute this small table to every executor in the cluster. This way, the larger table doesn't need to be shuffled based on the join key, which can significantly reduce the computational overhead. By avoiding the shuffle process, this method not only improves performance but also helps address potential data skew issues that might occur during a regular join. Broadcast joins are often the most effective solution when one side of the data is relatively small and manageable. Another strategy is filtering early in the processing pipeline. If you can eliminate unnecessary data before performing resource-intensive operations like shuffling, aggregating, or joining, it can lead to a substantial reduction in the amount of data that needs to be processed. For instance, if a specific column such as hotkey isn't required for a particular calculation, removing it before the group by operation can speed up the overall job. This approach helps keep the data size under control and makes the execution more efficient. The cleanest fix in many cases is to prevent unnecessary shuffles from happening in the first place. By optimizing the query plan and ensuring that data is filtered or transformed early, you can avoid costly operations later on. This proactive approach not only saves time but also contributes to better system performance and resource utilization. A common mistake is thinking that repartition alone fixes skew. While repartition can redistribute data across more partitions and help with general imbalance, it doesn't automatically split a single key that causes the problem. If all records have the same hot key, the hash of that key will still point to one partition during a key-based shuffle. This means that even after repartitioning, the hot key can still end up in just one partition, causing one task to handle most of the work. This is the key difference. Repartition can improve the number of partitions or their distribution before certain operations, but it doesn't solve true key skew. One key will still land in one partition unless you change the key strategy, use salting techniques, broadcast the smaller side of the data, filter out unnecessary records, or redesign the operation itself. Let us finish with the practical rules. First, identify skew early using the Spark UI. This tool provides valuable insights into how your tasks are performing. Pay attention to task duration, which can indicate if some tasks are taking longer than others. Also, check for spill, which happens when data exceeds memory and has to be written to disk. Garbage collection time is another important metric, as long pauses here can slow down your job. Lastly, look at idle executors, which might suggest that some nodes are underutilized while others are overloaded. Second, expect skew in real-world data. In practice, business data is rarely perfectly balanced. Data often comes from multiple sources, and each source may have its own patterns, leading to uneven distribution. Recognizing this early can help you avoid performance issues down the line. Third, remember that hotkeys destroy parallelism. When a single key is responsible for a large portion of the data, it can become a bottleneck. This single key can turn what should be a distributed job into a single task process, significantly slowing things down. Fourth, salting can improve data distribution, but it adds complexity and may require reaggregation. The idea is to add a random value to the key, spreading the load more evenly across partitions. However, this technique needs careful implementation, as it can complicate the logic and require additional steps during processing. Fifth, broadcast joins are often the cleanest fix when one side of the join is small enough. By broadcasting the smaller dataset to all nodes, you avoid shuffling large amounts of data across the cluster, making the join more efficient. This approach works well when the size of the dataset fits comfortably in memory. If a Spark job never finishes, look for skew first. Do not assume that adding more cluster resources will solve the issue. Sometimes the problem lies in the data design or the way keys are distributed. Fixing these underlying issues is more effective than simply increasing resources. Spark scales computation, not broken assumptions. It's designed to handle large-scale data, but it can't compensate for poor data modeling or inefficient key distribution. Understanding these principles helps you build more reliable and performant Spark applications.